Okay, we're live streaming on YouTube Live. So we will start at 8 o'clock or 9 o'clock. So let me know if you can hear me. You can also sign in. Okay, good. That's a good sign.
So are we gonna be over here from now on, or are we going back over to rendezvous?
Again?
Are we gonna be over here from now on, or are we going
Yeah,
back over to?
it's official as of this morning. So I don't have to worry about the Zoom crashing on us anymore. So I'm going to go to my office and send an email. Did you see any other people?
I don't think I put on my way.
You didn't see the other?
Yeah. I was worried I wouldn't be able to find this, so I came here before class. Yeah, that's what I did too. I have a lot here in this building, and I got lost looking for it too. This building is very confusing. Yeah, not exactly a consistent layout. Yeah. Still though, I actually almost prefer we locate the class here, that other classes forming in the sort of lower campus area. It'd be nice not to have to rush back and forth between rendezvous. Yeah, but I like it in rendezvous because that's where I'm staying. So I just have to roll out of bed and go down the flight of stairs. Yeah. My first class is in a business administration building, and then I had to run all the way back to rendezvous and then all the way back down here to physical science for this class. So. That's what it is. Gotta do what you gotta do. So. I think he said we'll be in here tomorrow. Really? Yeah. Well, I think I'm in all places in my building where this is the plan for. It would make more sense for it to be here, logically speaking. Yeah. So were you able to get like any of the lecture yesterday? No. So, yeah, so basically once this screen froze, we never saw it, not until the lady from down there. Or I did. Oh, that was you? Yeah, it was me that went down there. Oh, yeah. Yeah, so basically once the screen froze, we didn't get nothing until you went down there. Yeah. I tried to piece what I could together, like a little tail end of it, but I'm just gonna have to read the chapter. Or can you go back and rewatch the YouTube video? Probably, yeah. I'll figure it out. I think we have exam next week. Yeah. Wonder if this was like a sudden change since before we got the email like an hour and a half before class.
Hope they didn't get lost. Okay, it's 9 o'clock. We'll go ahead and get started on improper integrals. Okay, so it's official as of this morning. From now on, we'll have our classes in room 307 of the physical science building. And so our online will always be YouTube live from now on, so no more Zoom. Okay, chapter 7, section 8, part 1. On Friday, we'll do part 2 of chapter 7, section 8. But in part 1, we'll discuss improper integrals of type 1. So those can be in 3 different classes. So the first one, part A of type 1, suppose a function f of x is defined on the interval from a to infinity, such that the definite integral of f of x from a to t exists for every real number t greater than or equal to a. Then the improper integral of f of x from a to infinity is defined to be the limit of the definite integral of f of x from a to t as t approaches infinity, provided the limit exists. Okay, part B, this time we suppose a function f of x is defined on the interval from negative infinity to b, such that the definite integral of f of x from t to b exists for every real number t less than or equal to b. Then the improper integral of f of x from negative infinity to b is equal to the limit of the definite integral of f of x from t to b as t approaches negative infinity, provided the limit exists. Okay, so the improper integrals of f of x from a to infinity and an improper integral of f of x from negative infinity to b, they are called convergent if the corresponding limit exists, and divergent if the limit does not exist. Okay, under part C, we'll find my first typographical error of the day. Under part C, if both improper integrals, so the improper integral of f of x from a to infinity and the improper integral of f of x from negative infinity to a, if both of them are convergent, then it turns out that the improper integral of f of x from negative infinity to infinity is equal to, this upper limit should be a in this case. So the improper integral of f of x from negative infinity to infinity is equal to the sum of the other two improper integrals. So for the part C, we need the value a to be the same because we're accounting for all numbers between negative infinity and positive infinity. And a could be any real number in the interval. So if you just got here, all I did was read the first page, which is the definition of improper integrals of type 1. And they can be in one of three classes. So the first class is the improper integral of f of x from a to infinity. The second class in type 1 are the improper integrals of f of x from negative infinity to some real number b. And then class C, if both of the classes of improper integrals are convergent, then the improper integral from negative infinity to infinity is also convergent and equal to the sum of the other two improper integrals. So, and then one other thing just to point out, if each of those limits exist for the improper integrals, we say that the improper integrals are convergent because they are equal to some finite number. And if the limit doesn't exist, then they are divergent. So divergent could mean that the limit tends towards either infinity or positive infinity. Another way that a limit doesn't exist is that it bounces around between different finite numbers. Okay, so we're ready to work on our first example. So I'll give you a couple of minutes on this one. This one is not an improper integral, but I think the results of computing the definite integral will be of use a little bit later today. So I'll give you 2 or 3 or 4 minutes to work on this and see what you come up with. Here we're letting r be a non-negative number, so r is greater than or equal to 0. And compute the definite integral of 1 over x dx, where the limits of integration are e to the r for the lower limit and e to the r plus 1 for the upper limit. So give that a try. All done? Oh. So if you're watching on YouTube, if you find the answer to that, you can type it in. It won't take much to type it in. Try to resist the temptation of using a high-powered calculator. So how many are on the right track, do you think? Well, let's go ahead and all right, equals, what's an antiderivative of 1 over x with respect to x? Natural log of the absolute value of x. So natural log of the absolute value of x. And then we evaluate that at the limits from e to the r for the lower limit and e to the r plus 1 for the upper limit. So we get the natural log of e to the r plus 1 minus the natural log of e to the r. Using properties of the logarithms, what can we write next? If the natural log of something, if we have the natural log of something minus the natural log of something else, how can we write that? So the property for all logarithms, not just the natural log, but I'll just write the natural log of a minus the natural log of b, that can be written as the natural log of a divided by b. It's, in a nutshell, what one of the properties of logarithms is. So we'll do that here. This is the natural log of e to the r plus 1 divided by e to the r. And from here, we can do a couple of things, as in one or the other. We can simplify the argument of this logarithm using one of the properties of exponents. So here's the property. If you have a base number b greater than 0 but not equal to 1, so if you have b to the m divided by b to the n, that's equal to b to the m minus n. So we have that sort of thing in this argument of the natural log. So we apply this rule, one of the rules of exponents, the base number e, and we have r plus 1 minus r. So r plus 1 minus r is just 1, so we get the natural log of e to the first. And what's the natural log of e to the first? 1. Using another property of logarithms, the natural log of some number raised to a power, that's equal to the power 1 times the natural log of e. The natural log of e is just 1 because here's another property of logarithms. If you have a base b logarithm, and if the argument is b, remember what a logarithm is? A logarithm is an exponent. So this property, the log base b of b, that's equal to the exponent that b must be raised to in order to get b. So b raised to what power equals b? B raised to the power 1 equals b. So b to the first equals b. So the base of the natural log is e, so the base e logarithm of e is equal to 1. So this is just 1 times 1, or 1. Okay, so we get an integral that equals 1 on the interval from e to the r to e to the r plus 1. So how many such intervals are there? Okay, if we start with r equal to 0, then the lower limit is 1. When r is 0, e to the 0 is 1. And the graph of 1 over x for values of x greater than 1, the graph of 1 over x looks something like this. It's asymptotic to the x-axis, right? So it gets closer and closer to the x-axis. But intervals of the form e to the r to e to the r plus 1, how many of those intervals are there? So if I start with e to the 0, which is 1, and then go to e to the 0 plus 1, or e to the first, and then go from e to the first to e to the second, right? If I just increase the exponent by 1, when do I stop? When do I stop? When can I stop? I can't ever stop, right? Well, but the idea is on each of those intervals of the form that have endpoints e to the r, and then the next one is e to the r plus 1, what's the area of each one of those? Each one of those areas is 1. So this area is 1. Then on the next interval, from e to the first to e to the second, we have another area that's equal to 1. And then on the next interval, e to the second to e to the third, I have another area that's equal to 1. And I never stop. So can you make a conjecture on this improper integral of 1 over x from 1 to infinity? So if I just keep adding 1 plus 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 1 forever, what do we say about that?
Divergent.
It's divergent to infinity, right? The limit does not exist as a finite number because I keep adding 1 forever. So the area below the graph of 1 over x from 1 to infinity is unbounded. It's an infinite area, if you want to call it that. So I would make the conjecture that this improper integral is divergent just based upon this previous experiment. That's what I conjecture. So this diverges. Hey, but we can actually prove this. If you remember on the previous page, we're going to think of this class of improper integrals from 1 to infinity, 1 over x dx. Then we write it as a limit as t approaches infinity of the definite integral from 1 to t of 1 over x dx. And this will be the limit as t approaches infinity. An antiderivative of 1 over x is the natural log of the absolute value of x from 1 to t. So this is the limit as t approaches infinity of the natural log of t. Since t is assumed to be positive, I'll just omit the absolute value symbols, and then minus the natural log of 1. The natural log of 1 is just 0. So as t approaches infinity, the natural log of t also approaches infinity. So it's not really mathematically correct to say this equals infinity, because infinity is not a number, it's just a destination. But for convenience, we refer to this type of divergence as a limit to infinity, or an unbounded limit. The natural log function increases very slowly, but it does approach infinity, even though it gets to infinity at slower and slower rates. Okay, let's look at the next improper integral. So this one is class 2 of type 1. This one is the improper integral of 1 over 1 plus x squared dx from negative infinity to 0. So let's write it as a limit. This time t approaches negative infinity. And we write a definite integral. We put t as the lower limit and 0 as the upper limit of 1 over 1 plus x squared dx. Okay, we've learned how to find an antiderivative of something of this form, 1 over 1 plus x squared. Do you remember what the antiderivative of 1 over 1 plus x squared is? It's the inverse tangent of x. So we'll write this as the limit as t approaches negative infinity, and then the antiderivative is inverse tangent of x, and then the limits are from t to 0. Okay, so in the next line, the limit as t approaches negative infinity, and then the inverse tangent evaluated at 0, minus the inverse tangent of t. The inverse tangent of 0, so the angle whose tangent is 0, right? So this is the limit as t approaches negative infinity of 0 minus, and what's the limit of the inverse tangent of t as t approaches negative infinity? I can sketch a graph of the inverse tangent. I'll squeeze it in here a little bit. So the inverse tangent has a horizontal asymptote. Whoops, that's supposed to be positive pi over 2. And another horizontal asymptote at negative pi over 2. So x-axis, y-axis. Horizontal asymptote. So roughly, this is sort of what the inverse tangent graph looks like. So here we're using t, but just think of what x would do as x approaches. As x approaches negative infinity, what does the inverse tangent approach? Negative pi over 2. Yep. Okay, so we have 0 minus negative pi over 2. Well, that's the result of the limit. I really shouldn't combine the limit notation with the limit itself. So this is still inverse tangent of t. Okay, but we now know that this is just 0 minus negative pi over 2, or pi over 2. So this one converges, and it converges to pi over 2. Well, if we were to compute the class 1 improper integral, that is from 0 to infinity of 1 over 1 plus x squared, we would essentially just go through this same sort of thing that we did above, just this time going from 0 to infinity. This will also be equal to pi over 2. So what did we learn on the first page that I had? So class C, if the improper integral of a function from negative infinity to a, in this case 0, if that's convergent, and if the improper integral of the same function from a to positive infinity is also convergent, then what does that mean? That means the improper integral of class C from negative infinity to positive infinity of 1 over 1 plus x squared dx, that's equal to the sum of the class 2 improper integral and the class 1 improper integral. And so pi over 2 plus pi over 2 is equal to pi. Pretty neat, huh? So I don't know, it's, if you think about, well, pi is the ratio you get when you divide the circumference of a circle by its diameter. So getting a class 3 improper integral to equal that number sort of seems interesting, at least. Okay, let's look at another example. Let's evaluate this improper integral. The integrand is 1 over x to the third. And we want to evaluate the improper integral from 1 to infinity. So I think you know enough to work on this for a couple of minutes. You know how to find an antiderivative of 1 over x to the third. So just rewrite this as the limit of the, as t approaches infinity, of the definite integral from 1 to t of 1 over x to the third. And then evaluate that definite integral from 1 to t for the integrand 1 over x to the third. Do that for a couple of minutes, and then we'll compare notes. Okay, so we'll write it as the limit as t approaches infinity of the definite integral from 1 to t. And I'm going to rewrite 1 over x to the third as x to the negative 3 dx. And then we use one of our antiderivative formulas. The limit as t approaches infinity. And then an antiderivative of x to the negative 3 is x to the negative 2 divided by negative 2, right? Is that what you got? Because negative 3 plus 1 is negative 2. Divide by the same number. And then from 1 to t. So let's make this look a little nicer. So the limit as t approaches infinity. I'll write this as negative 1 over 2x to the second from 1 to t. Okay, so the limit as t approaches infinity. So the first term, negative 1 over 2t to the second, negative 1 over 2t to the second, and then minus a negative 1 over 2 times 1 squared, or 1/2. So we're almost done. So we get the limit as t approaches infinity. Since I'm just going to rearrange what we have inside the brackets, since I'm subtracting negative 1/2, that's positive 1/2. We'll write that positive 1/2 first, and then minus 1 over 2t to the second. So 1 over 2 is unaffected by what t does, but what does 1 over 2t to the second get close to as t approaches infinity.
0.
Yep, 0. So this is 1/2 minus 0, or 1/2. So this improper integral converges to 1/2. So converges to 1/2. Okay, here's another improper integral. So you can maybe get this finished in a couple of minutes. So I'll give you a couple of minutes. Hey, it's been a couple of minutes. What did you come up with? It's an answer. Okay, let's do this one. Let's write it as the limit as t approaches infinity of the definite integral from 1 to t. And I'm going to rewrite 1 over the square root of x as x to the negative 1/2. And then an antiderivative of x to the negative 1/2. X to the negative 1/2 plus 1 divided by negative 1/2 plus 1. So x to the positive 1/2 divided by 1/2. And so if you divide by 1/2, that's equivalent to multiplying by 2. So we get an antiderivative of 2 times the square root of x from 1 to t. So we'll evaluate that. 2 times the square root of t minus 2 times the square root of 1, which is just minus 2. So as t approaches infinity, the square root of t approaches infinity. So this, in an informal way, we say this is equal to infinity. But really, we say the more formal way is the limit does not exist as a finite number. it tends towards infinity. So it's divergent. Okay, are we all in agreement? Okay. Hey, let's look at a class of functions determine the values of p that the improper integral of 1 over x to the p as as x goes from 1 to infinity. Determine the values of p where that integral converges by considering the 3 cases. So the first case, assume p is less than 1. So our improper integral from 1 to infinity of 1 over x to the p, I'm going to write it as x to the negative p dx, because we can apply a antiderivative formula to x to the negative p. But this is the limit as t approaches infinity of the definite integral from 1 to t of x to the negative p dx. Hey, so an antiderivative of x to the negative p is x to the negative p plus 1 divided by negative p plus 1. And then evaluate this from 1 to t. Since p is less than 1, another way to write negative p plus 1 is 1 minus p. So I'll do that first. So the limit of x to the 1 minus p divided by 1 minus p from 1 to t. So if p is less than 1, what does that tell you about 1 minus p? Greater than 0, right? Okay, so let's evaluate the definite integral from 1 to t. Oh, we get t to the 1 minus p over 1 minus p, and then minus 1 to the 1 minus p is just 1, so 1 minus 1 over 1 minus p. So what can you say about this limit, since this exponent is positive? Since 1 minus p is greater than 0, the limit of t to a positive exponent diverges to infinity, right? So this is divergent. This is just a finite number, but this denominator is positive, so this diverges. Hey, we saw that earlier. Remember the the 1 over the square root of x that we just did? Is that the one we just did? Yeah, we found that that is divergent. So 1 over the square root of x is x to the negative 1/2. And so the p-value is 1/2, which is less than 1, and it diverged. So anytime you have 1 over x to the t for an improper integral like this, if the exponent p is less than 1, then you can automatically know that it diverges. For p equals 1, we already did that one. So when p equals 1, we're just looking at the improper integral from 1 to infinity of 1 over x dx. We already showed that this diverges, right? So there's just one more case, and that is when p is greater than 1. So when p is greater than 1, so from 1 to infinity, we'll write this as x to the negative p again, dx. So this is the limit as t approaches infinity of the definite integral from 1 to t of x to the negative p dx. Okay, so we get an antiderivative of the same form that we saw earlier. So the limit as t approaches infinity of x to the negative p plus 1 over negative p plus 1 from 1 to t. So in the next step, I'll do a couple of things. I'll replace x with t, but I'll also change the exponent to 1 minus p. So we get t to the 1 minus p over 1 minus p, and then minus 1 to the negative p plus 1 is just 1 over 1 minus p. Hey, so if p is greater than 1, what can you say about the exponent 1 minus p? It's negative, right? So 1 minus p is negative. So if you want, you can think of this as the limit as t approaches infinity of 1 over t to the p minus 1, right? We're just taking the negative of that exponent. And then times 1 over 1 minus p. And then this minus 1 over 1 minus p is the same as plus 1 over p minus 1, right? And in this denominator, since p is greater than 1, p minus 1 is greater than 0. So 1 over t to a positive exponent approaches 0 as t approaches infinity. So this term goes to 0, and so the limit is it converges to 1 over p minus 1. Okay, that's all we have time for today. On Friday, we'll also be in section 8 of chapter 7. And from now on, our classes will be in room 307 of the physical science complex. And the online will always be YouTube live from now on. So that's all for today.